Okay, so hi everyone, and thank you for coming to this paper Colloquium. So today we have Dmitri, whom probably quite a few of you know because he's working here as a theory department at ABC, and he's going to tell us about LHAASO results from healthcare observations, which were released actually this month. So, thank you.
Yes, thank you very much. I will try to explain you the first sets of results which came from the modern gamma ray detector, which called LHAASO. Its results was released on this first LHAASO symposium in China. And here, I just will explain you relation why we're doing it. Here in APC, we have a small group who joined this collaboration from French side, and we just joined recently. So most of this result is done without our participation, but I will try to summarize where this experiment is now. So I will start with small introduction of gamma ray astronomy. I will come to this detector, this new generation Otto-Cherenkov detector, which was built to do two kinds of physics, gamma ray astronomy and cosmic ray physics. And what I will talk today is only gamma ray astronomy. So the cosmic ray physics would be released later. So the first thing I will discuss for the data would be first catalog of the sources, which consist mostly of pulsar-wind nebula with some fraction of supernova remnants and star clusters. Then, if we take out the point and extended sources from the data, the remaining part which they see is the diffuse galactic emission, which is very important contribution where we could try to get contribution of cosmic rays in the galaxy. And then maybe one of the most highlighted things was this gamma ray burst, which happened last year in October, and this one, which was seen by LHAASO. So it's a very fortunate in time that just a few days ago, there was a release of the results of this gamma ray burst in science paper by LHAASO, and now it's open to discuss this. So I could discuss it in the talk. So let me start with just small introduction for those of you who are not familiar with gamma ray astronomy. There are several kinds of detectors which detect gamma rays. There are space-based detectors, and there was the pioneering detector Egret, and then there are few, but most famous are Fermi telescope. This is a satellite which go around the Earth with large field of view, very large duty cycle, and good angular resolution, good removing of the background due to anti-coincidence shield. So there is a kill background of the cosmic rays in the detector, so they could really measure photons one by one. And this is a beautiful telescope, but the main restriction for the highest energies is area. So because this is satellite, the size is 1 meter squared, so you could not measure too many high energy photons. If you go to higher energy and want to measure a lot of high energy photons, we have to go on the ground. And the most popular and most successful way to do it is Cherenkov telescopes. So here you see the LHAASO telescope, which consists of 4 smaller ones, which originally was a big one in the middle. And we have here our colleagues in APC from the LHAASO group who are working on this telescope. And in the future, there would be much bigger version of this telescope, which is in construction now, which called CTA, Cherenkov telescope array, which would consist of sets of telescope on the south and on the north, covering all the sky with this kind of telescopes. So these telescopes, they have very good angular resolution, very good energy resolution, very high detection area, because this is a Cherenkov pool on the ground. But the kind of disadvantage is the small field, relatively small field of view, which would be a bit larger for CTA, but few degrees, and the duty cycle, because these telescopes could work only in the night, and the good data in moonless night. So still today they detect even in the moon time, but the quality of data is reduced. So this is a Cherenkov data. And now finally, at the even higher energies, if we want to go, we have to go to extensive air shower arrays. And there was a long story about this kind of observations, which was not very successful in the beginning because of very high backgrounds, but then people learned from it, and starting from Tibet IS Gamma and Hawk, and now with the LHAASO, this kind of technique is in the game. And the advantage is a large field of view, large duty cycle, but of course, the angular resolution is worse than for Cherenkov telescopes. And for early detectors, the area was very small, but now with LHAASO, it's come to kilometer square size. So it's really compete with the Cherenkov telescopes. So now these are typical catalog of the sources which exist from the Fermi telescope. There are thousands of sources, and then from LHAASO or from Hawk, there are many, almost 100 sources from each over the sky. The gamma rays are not freely coming to us from the sources to our detectors because they are attenuated on the way, interacting with the different backgrounds. And for very high energy, most important is SIMB, cosmic microwave background, which is everywhere in the universe. And at so this drop of attenuation length at very high energy is due to SIMB. But here you see, even before that, the probability to come is not one because of infrared and optical backgrounds, which come from the stars in the universe and from the dust in the universe. So these are backgrounds for these measurements. Nevertheless, there are already hundreds of sources which are measured at very high energies, as you see here, compared to thousands of sources at low energies where there is no attenuation of the gamma rays at all. And before this data, which I will talk about today, there was just few sources at very high energy, bigger than the 100 TeV, and these very high energies are definitely of galactic origin because of the interaction with SIMB. If you want to hundreds TeV or PV gamma rays come to us, they should come from very, very nearby universe. So for the other side, it's important sometimes to detect something which is very bright but very localized in time, like gamma ray burst. And for gamma ray bursts, the important thing is to either to have a very large field of view to detect gamma ray bursts, to be lucky, or to very fast move to the direction of gamma ray burst when it's reported. So the Cherenkov telescopes, they have very small field of view, but all the modern telescopes, they made in the way that they could quickly come to the direction of the gamma ray burst, moving the telescopes. And for this water Cherenkov detectors like HAASO or LHAASO, they just passively observe, but very big fraction of sky. So when gamma ray bursts happen, if it's happened in this fraction of the sky, it would be detected if it's above threshold by this kind of the instrument. And I will show you the detection of the LHAASO. Now let's come to this detector. So detector is constructed in the high altitude mountains in China. And okay, there is big list of scientific goals for gamma ray astronomy and for cosmic rays, and even for the physics beyond the standard model. And detector consists of several sub-detectors. So in the center, there is a big water pool. And here in this picture, you see interior with detectors in it. And it's surrounded by the set of the detectors, which are two kinds of detectors. One is surface detectors, which is shown here, which are detectors which would detect electromagnetic radiation of the cosmic rays and gamma rays. And there are underground muon detectors, which are with the blue things here, located again everywhere, which are covering like something like 4% of the area of the full detector. And this is a key moment which allows this detector to be so much sensitive to high energy gamma rays that they are able to discriminate cosmic ray background very efficiently due to these muon detectors. Now, this water pool detector, it's has two kinds of detectors. One is a big photomultipliers, 20-inch, and another is the small ones, 3-inch, and this is to recover big energy range. So, yes. Depths of few meters. So this just to get when the air shower or high energy gamma ray come to the detector at very center, this very large photomultipliers are saturated, and then one could use these small photomultipliers to get a signal in the detector. So it's to increase the range of detected signal. And for the kilometer detector, as I told, it's a very nice device to distinguish air showers from the gamma rays. For example, here you could see 1 PV cosmic ray, and in this 1 PV cosmic rays, it's detect big fraction volume of the detector of the surface detectors, but also circles here are muon detectors underground. So here all over the rear, many of them are give a signal. While for gamma rays, it's not so. There are very few gamma ray, very few muon detectors are still working because these are muons which are produced at this energy by original gamma ray with P gamma in the atmosphere, but very few. And then there is an electromagnetic signal which is similar in size to this one. So these are both PV events, but this is a cosmic ray and this is gamma ray. And discrimination factor is better than 10 to minus 5, which is very good at these energies. Also, there is a third kind of the detectors, which are wide angle telescopes. These are used to discriminate composition of cosmic rays, and this data is not yet released. So they're just detecting cosmic rays in this way. So for water Cherenkov detector, the discrimination come by the shape of events. So they don't have separate mu detectors, but so the typical proton is widespread signal, the typical gamma is widespread. So in this way, you could discriminate depending on how many detectors hit between 1% to 10 to minus 3 of the signal. So it's very similar to what was done in the Hawk detector. And for this kilometer square detector, it's much better. So as you see here, so that at 100 TeV it's 10 to minus 4, and at closer to PV it's go to below 10 to minus 5. And this allow to really do gamma ray astronomy at very high energy. So this experiment has a connection, networking connection to many other gamma ray and neutrino experiments in the world. And you see here, Antares and Kilometer CubeNet is connected to our institute as well. And here is maybe one of the important pictures. It's comparing the sensitivity of this detector to the other existing and future detector in case of CTA. And comparison done as a typical in this kind of picture, 50 hours of the Cherenkov telescopes compared to 1 year of this kind of the water Cherenkov detectors. So, but this 1 year, they cover all sky, and typical Cherenkov telescope, 50 hours per year spent for given source. So this is a kind of honest comparison, but every method has its advantages, of course, and they are very complementary because this water pool, as you see, it's sensitive, better sensitive at very high energies, but less sensitive at low energies, and could see all the sky eventually. And if something is very bright is going on, so then Cherenkov telescope could look. So it's very similar to what could be done with Fermi, but at high energy. And at very high energies, around 100 TeV, this is unbeatable way to detect gamma rays. So these are just first papers which was published recently for Pevatrons, Cygnus bubble submitted, and Crab nebula and gamma ray burst. Now I come to this new release which was done last week on this meeting, the first catalog of the sources. So the new release concerns the period of the construction of the detector, which was 0.5 kilometer square, 3/4, and then full detector, which more or less equivalent to 2 years, a bit more, around 2 years of the full detector. And for a bit shorter period, equivalent for the water Cherenkov pool, because they constructed first 1 pool, then 2 pools, and then the pool 3. They estimate background with the Planck dust maps, so in very simple way, on the just looking on the line of sight, summarizing the signal, and when they do the background estimate for cosmic rays, they excluded all the known for the sources for the detector and galactic plane, and then estimate background from this region. And then they do this kind of the likelihood analysis in the energy bins, and this is the result for the water pool and for kilometer square detector. So this is the sky as they see it in the equatorial coordinates, they see only those which is above the detector. And then if you move to galactic coordinates, they couldn't see galactic center and this part of galaxy, but they could see the rest. And you see here, this is low energies below 25 TeV, and this is high energies above 25 TeV. See here sources in the galactic plane and some other sources outside of galactic plane. So then there is a cross calibration between two detectors to see if they see the same sources or not the same sources, which spectra they see, and so on. And out of 90 sources together, 54 are the same, and the rest are not the same. So the majority is the same, but not completely. And for kilometer square detector above 25, they have 75 sources, and out of them, 43 are seen above 100. So this is the best sensitivity range for this detector. So they see very big fraction of sources at this energy. And this is important thing, because before LHAASO, there was known only 4 sources above 100 TeV. And now we knew 43. So it's 10 times more. So in first data, they released 12 sources, which included 4 which detected before, and 8 which they detected in the very, very first set of data. And now they increase it to 43. So this is really coming to the real catalog of sources above 100 TeV with morphologies and spectrum and so on. So the catalog is public, it's published online. So with all the characteristics, I don't have time to discuss it, with the test statistic, which more or less indicate how significant is the detection of given source. And the sky maps, so this is in galactic plane below 12 degrees, all the possible sources. And above 12 degrees, they see 4 sources which are AGNs, which are seen at low energies, but not seen at high energies. You see here Markarian, 2 Markarians, and 2 other AGNs. And 4 sources which are actually probably 2 sources which are opposites. They are seen at very high energy, above 25 TeV, but they're not seen at low energies at all. So these are galactic sources which probably new kind of sources which are not seen at below 25 TeV at all. So, and okay, okay, they associate many of sources with known sources. There are some new sources which are like one sort of catalog, are completely new sources which was not seen before. And most of sources, majority of sources are pulsar connected with the pulsars or pulsar wind numerals. So these are leptonic sources, and this is the catalog of the pulsars with the age of the pulsar and energy of the emitted by the pulsar. And you see they see the brightest with youngest age, but not all of them, but many of them, and they saw first millisecond pulse. Okay, so that's more just to show that there are many sources at very high energies in the galaxy with different spectral index. So now this is this first catalog. So at low energies there are 69 sources, at above 25 to 175, at about 143 sources. Now yes.
Since most of these sources are galactic, how do you distinguish from extended emission from source?
In this catalog, okay, I will talk about the extended emission later. In this catalog, by definition, they take only sources which has size smaller than 2 degrees. So they could be extended, but not more than that.
So definition.
Yeah, that definition, how they distinguish, because at some point you have to cut. There are some sources which are bigger. So pulsar wind nebulous. So okay, I don't have time to discuss this, all the talks which was in the meeting in details. So you could look in the slides later. This is just from historical different sources which is which was known before, most of them by Hess, and identified and probable candidates. And okay, and this another famous source is this Geminga with the HAASO, which was very unexpected and detected by Hawke with diffusion coefficient, which was suppressed significantly. So there was this then theory constructed how you could explain this kind of suppression of the diffusion coefficient and different pulsar wind nebulas at different ages and different stages could be explained if they are inside of the supernova remnant, just going outside or really outside of. And different subclasses of the pulsars and pulsar wind nebulas are detected by LHAASO. So 35 sources associated with pulsar. Okay, there are a few interesting examples. One is crab. Okay, this is the kind of the standard source for gamma ray astronomy, which is shown here. The interesting thing that probably LHAASO start to see deviation from this leptonic part here, which require a bit more statistics. So, but in the first data, they already see something above the tail of expected leptonic emission. So there could be speculations of different kind what it is. Okay, this I probably skip. There are a few more interesting sources which I don't have time to discuss, but there was a special talks on the meeting for Geminga. What they found on top of this few degrees halo, which was found by Hawke, they found 10 degrees halo, much bigger, but less pronounced, but still it's significant in the detection. And this halo is anisotropic, so it's not symmetric on the 10 degree scale. Okay, they just declare that it exists, but there is no still reasonable models for it. But it's on discussion now, this very hot topic. And another interesting source, this one is one which is outside of galactic plane at 17 degrees from galactic plane, this millisecond pulsar, which have this kind of jet going out with electrons. So another new class of the sources. For supernova remnants, okay, they detected few of them, but at the very high energy tail. And maybe the interesting one is Gamma Cygni. They detected it up to 100 of TeV. And the important thing that this energy, as the model, it could not be explained by the leptonic emission. So there could be only easy way to explain this is the hadronic component. But still, it could be different origin, either it comes from molecular clouds or it's come directly on the shell of the supernova. So it's not yet clear. Another topic is the star clusters. The galaxy is full of the star clusters, and these star clusters are very good sites to again accelerate cosmic rays and produce secondary gamma rays in hadronic emission. And one young cluster is in the Cygnus region, and they discuss the Cygnus cocoon with quite good measurement. And again, there is some in the center of cocoon, there are, of course, there are few sources there, but on top of that, there is a diffuse emission in the center, which is more compact on scale of few degrees, 3 degrees. And then there is a big bubble outside, which has a radius of 10 degrees. So this also has to be studied theoretically what it is. And then, okay, this is another one, another of these sources, which has morphology which is quite different at 100 TeV, at 25 TeV. Now I come to subject of diffuse emission. So how much time I have? Okay, so fine. So diffuse emission is much more, in some way, much more difficult than point sources because it depends on how you subtract the background, which is not easy. And okay, the idea is cosmic rays, which are accelerated by sources in galaxies, they diffuse in the galaxy and produce a diffuse emission and gamma rays in interaction with the gas. But at very high energy, the point is that very high energy diffuse emission could be produced in quite different ways than at low energies, because much smaller number of sources and different ways of propagation of cosmic rays. The first diffuse emission was observed in galaxy at high energies, was observed in 21 by Tibet IS gamma experiment, and you see it here. So they saw kind of galactic plane at, so this is 100 TeV, this is 400 TeV gamma rays. So they saw galactic plane in these different energies around few hundred TeVs, but outside of point sources. So they look for photons which are located more than half degree from the point source. And they saw this kind of diffuse emission. And there was a discussion that it's more than what the model predicts, but it's again the same question, how far you go outside of the sources. So here they go half degree outside of the sources. In LHAASO, they did a special analysis for diffuse emission where they reduce background significantly, more significantly than for point sources. For point sources, they use this kind of subtraction as shown here, which stay all the, as you see, 100% of gamma rays, more or more 100% of gamma rays remain in analysis, but with the price that there is quite a big background of cosmic rays, so they reduce like 10⁻⁴ cosmic rays, but this is enough for bright sources. For diffuse, it's not enough, so you need to reduce more. So, but the price you kill part of the gamma rays, so they kill like 50% of gamma rays and reduce more significantly cosmic ray background. And another point they do, they remove regions around the sources from analysis and consider diffusion emission only outside of these regions. So this is by itself, the procedure is not completely safe in some way, because in the central galaxy, you see all the regions around sources kill everything around 1 degree of the galaxy. So you look only on the tails of diffuse emission and not have access to the central part of diffuse emission. But that's the way how analysis was done. And what they found that if you take gas and just consider line of sight coming through the gas interaction, it's not enough to explain the signal they observe in diffuse emission. So the signal is always high. So whatever it is, it's a separate story, but experimentally, the amount of diffuse emission is higher than what expected from the Coulomb density of the gas. And that's what is shown here. This is inner galaxy, this is outer galaxy. So this is what you expect from the gas, and that's what they measure. They measure like 3 or 2 times more diffuse emission. Of course, you see the error bars are very large because this is just first data, and then they removed the main part of the signal together with point sources. So it probably has to be revisited with more data. But already this is very interesting. So I just, this is slide which I added for myself to try to point for you physics which is important here. So this is the flux which is measured in diffuse emission by LHAASO. This is outer galaxy, this is inner galaxy. And on the same figure I put, there was a paper by another Chinese guys who did a Fermi analysis exactly in this region. So with the same cards and everything the same. So this is the Fermi flux exactly from the same region as the LHAASO flux in inner and outer galaxy. And you see that if in outer galaxy, because there is no data here, it's very difficult to tell what is going on. In inner galaxy, it's much more clear. This part, which is Fermi, is measuring diffuse flux in the galactic plane. And this part, which you see in the LHAASO, measuring the region after the knee in the gamma rays, in the galactic plane. So knee is somewhere here. So this is before knee, and this is after knee. And you see the spectrum is here 2.5 multiplied by 2.5 in the central galaxy. In outer galaxy, it's maybe softer, but the important thing is what they measure here is the knee. And what is good, they have this water pool data, which is exactly located in this region of the energies, which is still under analysis. So when they're done with analysis of this data, they would put some spectrum here, which could be used for understanding of the thing. And from myself, I put here the limit from ice cube in neutrinos, that just to show that it's above all this data. So that's exactly what they want to say, that in near future they would put some data in this part of the pods. So one of the ways to explain data could be that at high energy, the galaxy is not anymore smooth. So this is a simulation from the smooth model of the cosmic ray propagation in the galaxy. And this is our recent simulation where we took propagation from many individual sources. And in this case, the diffuse emission much more clumpy compared to this case. And probably this could be seen in the data. Okay, so now I think I still have time to come to the last topic, which was released at this workshop, is detection of gamma ray burst of the last year by LHAASO. So this gamma ray burst, why it's interesting, I just, not everybody here is from gamma ray burst community, it's the brightest of all time gamma ray burst which happened last year. So for all many recording years, this is the brightest gamma ray burst. And it was so bright that Fermi gamma ray burst monitor, which is used to detect all the gamma ray burst routinely, was completely saturated. You see here in the brightest flare, it just saturated. So there is no data in here. So it was not, the signal was so bright that it was not able to measure it. So if this gamma ray burst would have isotropic energy, it would be 10 to 55x, so which is an enormous amount. But fortunately, there was many other smaller detectors in the sky, so which was able to measure even the gamma ray burst data in the peak, and from this one could get a total energy in the data. And this is just to show you bright gamma ray burst of all time. So here is the redshift, here is a isotropic flux, and you see this one is the brightest because actually it's quite nearby, but also very bright. And the probability that this happen again next year is 10 to minus 3. So such one we will never detect. Probably we could detect something in here, but not as bright as this one. So in this sense, LHAASO detector was very lucky that they was operating at that time. And as if you remember my previous slide, they see 1/7 of the sky. So they was really lucky with 15% probability they could see it, and they saw it in the field of view of detector. So for Cherenkov telescopes, there is disadvantages. The disadvantage that they have to repoint, but the advantage they could do it really if they have it in the field of view, and there was a few detection by Hess and Magic of the gamma ray burst in recent years at the high energy above few hundred GeV. Okay, but LHAASO, they saw it. So they saw it in both detectors, but the data which released now is only from water pool detector. So in this water pool detector, they detect with threshold 200 GeV, and they detected 60,000 photons. So this is if the similar thing would happen in neutrinos, this would be neutrino. This supernova neutrino in our galaxy would be seen by the today neutrino telescope with the similar amount of the neutrinos. So this is enormous amount of data, and you see they was able to detect very detailed life curve of the gamma ray burst with all the details. So there are few important things here. The first important thing that the biggest signal from the gamma ray burst itself, the original signal gamma ray burst, when it happened, there was nothing in the detector, in the LHAASO detector. So all this high energy emission is external shock origin. So it's not the original emission from the gamma ray burst. And okay, here the observed spectrum at different time, which could be reconstructed back to the just a simple power law spectrum. So it was very bright originally, and then it's shaded down with time, but it could be reconstructed by just one simple power law. And here is the signal in time, which could be divided in 4 intervals: very fast rise, then slower rise, slow fall, and fast fall. So there are 4 different time phases for the this gamma ray burst, and spectral index, as you see here, it's become from softer become harder in some way. So this very detailed information allowed to establish few things for with quite a good precision. First one is the gamma ray factor of the gamma ray burst. So what gamma ray burst is have a boosted emission of the in the electromagnetic channel, and from this fast rise you could estimate what is the Lorentz factor of all this emission, and this is 440 for this particular gamma ray burst, one of the biggest measured, but not the biggest. And then there is this kind of slow decay phase, which changes to fast decay phase, and this usually interpreted like you inside of the jet and then go outside of the internal jet. So this break allows to estimate how much jet is concentrated. And this angle for this gamma ray burst could be estimated, and it's very small, it's 0.7 degree. And if you remodel this isotropic, very huge emission 10 to 55 to be take into account this angle, the real energy of the gamma ray burst is something like 7.5 10 to 50x. So this is the standard one. So there is nothing special with this gamma ray burst. It's just a standard one, but seen inside of narrow jet going with very high gamma ray factor. And that's why we see such huge signal. So thanks to all that detailed structure of the signal which is seen in LHAASO, we could recover all these features. And another feature is now we're sure that because there was no signal in first 230 seconds, we are sure that this very high energy TV emission is not a prompt emission, but the collision with the shock, because in this when the signal was very high, there was nothing in the TV range, and the restriction that it's not prompt emission in this energy range is 10 to minus 5, so which is clearly strong limit. So here I just summarize this data all together. So if we take this gamma ray burst and we consider it model like it's gamma ray burst with narrow jet, we could measure the angle of the jet, we could measure Lorentz factor of the jet, and then the energy of the gamma ray burst is reasonable, nothing special. It's just because it's nearby and very narrow, and we look inside of the jet, it has this high energy. So that's bring me to the summary. So LHAASO is beautiful new detector which has very good sensitivity in the very wide energy range. So it's constructed in July 21 and operates since then in the full scale with almost 100% duty cycle, and it's above few TV, it's compatible to present-day Cherenkov telescopes in sensitivity for 50 hours compared to 1 year. And the same for CTA is above 20 TV. So for me, it's quite complementary instrument for the Cherenkov telescopes because they could combine measurements from both of them, could make a very beautiful science. And LHAASO presented first catalog of 90 of sources, and out of these 90, 32 are new ones. So there are new class of sources which are detected above 25 TV and not detected at low energy. There are many of them. So we have to study what are they. There's probably hadronic sources and so on. And there are 43 sources now above 100 TV out of 4 before LHAASO. And most of sources which are seen, majority of sources are either associated with pulsar nebula or having association with a pulsar or pulsar nebula, but not confirmed. So these 35 are confirmed, and then there is a fraction which are not yet confirmed, but majority, 65, I think, out of 90 are pulsars or pulsar nebulas. Then there are a few supernova remnants, star clusters, and few are not known, the new type of sources. Then for diffuse emission in the galaxy, as I told, the signal which is measured is above what is expected for just some light of sight dust. So which means that something interesting is going on and we need to reconsider the models for that. One of the ideas which we have here in APC is that it's a clumpiness of cosmic rays itself at these energies. Then it could explain this kind of things. Then one of the highlights of this experiment was that they was lucky and they detected brightest gamma ray burst of all time, this one. And as with 60,000 photons, they were able to establish in details the properties of this gamma ray burst. And I just want to mention that this is not end of the story for this gamma ray burst as well, because there is a kilometer square detector, which also detected this gamma ray burst, but these results are not yet public. So they would be published later, maybe this year or next year. So thank you very much.
Yes, so sorry. Thanks a lot, Dmitri. Then questions.
You show the development of the galactic stage. So if the 1 minute, so the next slide, I think. So here you've got the data and the LHAASO data, right?
Yes.
As you don't compare to the model here, did you say?
Yeah, I don't compare to models because, okay, I could proclamate my own models. I have even one slide here, but sorry? Yes, but this one this one should take with grain of salt. This what I did, I put this because when you have a limit on the given model, this is a limit for the signal from the model over the sky. It's not limit to the diffuse emission per centimeter square second steradian. So what I did, I assumed that the spectrum of this model, of Krag-Gamma model, in this fraction of sky, which is measured by LHAASO, go within 5 degrees and along the cell averaged, and then I could reshuffle one to another. So this is my so a bit up or down you could put it depending how you interpret this model.
Okay, but I think my question is, what's interesting is to know about the cutoff. There are two different cutoffs in the model. So I would like to know whether the data from LHAASO are compatible or incompatible with whether the two cutoffs for the ecosystem.
Yeah, that's I think one of these models is here. This is one of the models. So I think this one is a model which for the cosmic ray flux, same everywhere in the galaxy. So they have two models. One is cosmic ray flux shaped inner galaxy and outer galaxy differently, and the other is the same as measured here. So this is the flux as measured here. You see, it's already contradict to Fermi as we knew long before, and it's contradict to LHAASO here. But you could normalize it if you continue it literally to very high energy. You could normalize it here, but then you don't explain everything in between. So and
so the band below is another model with stronger cutoff and lower energy.
So this one.
Yes.
So this is I think a simulation from Gauss-Prop model of which was made by somebody.
So I think my question is, there is, do the LHAASO data now constrain the
Yes, they do, but one should be careful in it's model dependent analysis. So you could put, okay, if you're interested, I think I purpose removed I know. So for example, you could do this kind of thing which Chinese did, which I don't like. So you could take this model as it was, and then you by hand add in the middle some component to fit the total spectrum. So this is the phenomenological way to just say, I have another set of sources which contribute here. But I think it's not correct. So I think the correct way is to change these models to go like this.
We have few on Zoom, if you can, that's for. Is there anything in the room? Anything? So we have a couple of questions from Michael. So the first one is there any search for correlations with the Fermi bubbles?
No, not yet, because this is more difficult to LHAASO because it's a very big area. So I think it would require more time to study systematics, because big area more difficult to kill the background, because for the diffuse gamma ray background in the galaxy, what was done, they used the fact that the diffuse gamma ray background in the galactic plane accumulated to galactic plane, and then they use it to remove additional background of cosmic rays. And for the Fermi bubbles, it's not so easy to do so. So I think it would require some more time to work with systematic of experiment to talk about Fermi bubbles. But I think potentially it's possible, but just require more time.
And then the second one is longer, so maybe better if you open the chat and you read on the.
Yeah.
If you go up a bit. Yes, here. So this is the second question by Michael. So I can read it for the room. The second question is, for the AGN, it should be possible to place limits on axioms with some assumption. Is this being worked on? Maybe by yourself.
No, in LHAASO, there is a small group of theoreticians working with them who also do some beyond the standard model of physics, including axioms. So, but I don't know what is the progress of these people to do it. But I did not work on that.
Then there is the last one, which is more a comment than a question. It's for the proposed alto WCP. We show that on simulations at energies around 1 TeV, the costly rejection by having a muon detection part can be almost entirely replaced by new intelligent analysis with much better.
Yes, that's a good question. I think there is still way to go to this stage in LHAASO, and as in every detector, the first thing is to grab simple things which could be done in easy analysis, and then machine learning is something on the next stage when one want to improve, but having more data. So I think it would be done, but it definitely would require additional effort.
I have a follow-up question. So the data policy of LHAASO is fully private. So are they planning to release some data?
For the moment, as far as I know, they are private. I have no idea if they're going to release the raw data. I have no idea, but definitely not very soon, because they just started, so I think they, for the moment, private. But yes, raw data is difficult, as for every detector of this kind. Yes. But they are publishing catalog with properties of objects, and for interesting objects, they are planning to have a special papers. So the catalog paper is released, but for example, for Geminga and for any other popular and interesting objects where they have a new data which is interesting, they plan for every object have a separate paper with all the details of analysis.
Okay, there is another question by Yvonne. Yvonne, can you try to pick up?
Yeah, hi, can you hear me?
Yes.
Yeah, hi, Dmitri. I have a question on the 8 extragalactic sources that you showed. I don't remember now which slide it was actually.
Okay. So
yeah. No,
let's
the question is about, can we see some spectra, or are they going to come in a separate publication? I don't know. Can we know more about these sources?
Yes, sure. The roof, I think in the catalog for every source, there is a power law, roof power law for spectrum. Okay, for every spectrum catalog. So if you look for the catalog, there is a power law and the flux normalized at one point. But if you want detailed spectrum, so for many of sources, there would be the detailed studies, and then they would publish it.
Okay. But for the moment, that's only the power law spectrum.
Catalog, the power law and the power law fit to the spectrum and the amplitude.
Okay, thanks.
No more questions. Let's find Dmitri again. As usual, we can continue the discussion about helium and discuss right outside.
Thank you very much.
Thanks a lot.
Thank you. So I stop sharing.
Yes.